Okay, Assalamualaikum and good day to everyone. I hope you guys are still maintaining stay safe at home, but continuing do revision and attend all your online classes. Okay, today we are going to proceed chapter 3, magnetic circuit, which are the continuation of chapter 2 last time, electromagnetism. Chapter 2 and chapter 3 is really depend on each other, where last time in chapter 2 we learned about the electromagnetics, of course the definitions, what is the magnetic materials, magnetic flux, magnetic field, magnetic induction. So inside of this is the right hand rule, the Faraday's law of magnetism, and so on. So now we are going to proceed to the magnetic circuit. Okay, magnetic and electromagnetics effects play an important role in the design of electrical or electronic system. So all electrical and electronic system, to design that, we need both magnetic and electromagnetic effect. Most of the equipment depend on magnetic effect to function properly, and there is a great deal of similarity between electric circuit and magnetic circuit. So in order to do magnetic circuit later, we can use the electric circuit to analyze it. We will do in the end of this chapter. So for example, magnetic flux is a current. So MMF, magnetic motive force, is voltage. Okay, from this equivalent circuit, we can analyze it as magnetic circuit and electric circuit. So it's just the same, where the voltage here is the magnetic force, flux is I, and R is equivalent to S in magnetic circuit. Okay, the table shows the comparison electric circuit and magnetic circuit. You can look into it by yourself. So we will proceed to the next slide. Okay, magnetic field. Magnetic field we already covered in chapter 2, right? We can reproduce by putting a current through a coil. So on a coil, we input a current. So magnetic field can be produced. Magnetic induction occurs when a material is subjected to a magnetic field, and it's a change in magnetic moment from electron. So we have few types of material response. Respond to a field, ferro or ferromagnetic, which is have large magnetic induction, strong magnetic induction. Paramagnetic, poor magnetic induction, where diamagnetic or to oppose the magnetic moment. So for magnet, we have two types. Hard magnet have a large coercivity, and soft magnet have small coercivity. So what is coercivity? It is the resistance of a magnetic material to change the magnetization. So when have large coercivity, it's difficult to change in magnetization. So it's difficult to demagnetize or full the in other words, coercivity is the intensity that needed to demagnetize one fully magnetized material. Okay, type of magnetism. Just now we have ferro, very strong or have large coercivity, and paramagnetic is poor one, and diamagnetic oppose the magnetic moment. This is the strength of the magnetic field. So for use for electrical vision application, we have two tests, Epstein test and single slit tester, where Epstein test is to measure the power loss for electrical steel material. So we can plot the power loss, and we can measure the leakage flux at the joint and the limb of baby Epstein frame. So the with Epstein test, and other one is single sheet tester, the voltage can be calculated by using the equation V equals to 4.44 B and F and A, where the difference is just at the A, cross-sectional area, how to calculate the A. Okay, this is the other one that I told you just now, single sheet tester. But this one is for hard direction in steel strip. Just now, the abstract is more to soft magnetic material. The voltage formula is almost the same. Okay, what is flux? Flux produced due to the current in a wire or coil, where the wire and coil is act called electromagnet. So this is, we already explained about this, right? So a magnetic circuit is a closed path for the passage of flux produced by the magnetic force. So the line of force in magnetic field are called magnetic flux. So whereby the total line of force in magnetic circuit are produced by MMF, magnetomotive force. Okay. So you have a right hand rule, right? This one, your right hand. So show me your right hand. And the thumb going upward is your direction of current. And the other forefinger, this show your direction of magnetic field produced. That one is really important. You have to remember. Okay, and then the strength of the magnetic field measured by the flux density. So just now magnetic field gauge, the strength of it we call flux density B. So the good way to think about it by measure how many field lines in a certain area. So the stronger the field at the pole, more field line. So we call B, and the unit is Weber over meter squared or just Tesla. So we always use Tesla in our question. Okay, the formula of flux density. Flux density is defined as a flux per unit area. So B is equals to phi, or magnetic flux, we call phi over A, where the B is Tesla, magnetic flux, phi is in Weber, and A area is in meter square. So if the question gives you dimension, you have to calculate for the area first, and B and phi, we always just give the parameter like that. So example 1, for the core in figure below, determine the flux density B in Tesla. So this is B equals to phi over A. You can just put it and got the answer, right? So we can proceed. Okay, what is permeability? Okay, have you heard conductivity in electrical? So permeability is the same as conductivity, but in magnetism. So permeability is the ability of a magnetic material to produce a flux in a magnetic circuit formed by a magnetization force. Or in a simple word is how flux can be taken in a magnetic circuit. So when the material is said to have high permeability, when more flux can flow to it. So permeability symbol is mu, where the unit is Weber over area per meter. So permeability mu is equals to mu naught times mu r. What is mu naught? What is mu r? Okay, there's three types of permeability. Permeability of the material, mu. Permeability of the free space, mu naught. And this is constant, and this is the value that you should remember. Must be in your head. 4 pi times 10 to the power of -7. And mu r, ratio of permeability material to the permeability free space. Mu r is depend on the material. So different material have different relative permeability. Okay, now what is reluctance? So reluctance is the resistance to flow of magnetic flux. So in electric circuit, we call resistance resist the flow of current. In analogy, in magnetic circuit, reluctance resist the existence of magnetic flux. Same resistance, reluctance. So opposition offered by magnetic material to the flow of magnetic flux, we call reluctance. Again, reluctance is like the resistance. One in electric circuit, one is in magnetic circuit. Okay, the reluctance depend on the length of material, the cross-sectional area of material, and the permeability of the material. So this is the formula. So R is equals to reluctance equal to length over mu A, where we call rels the unit, or we can also use as AT over Weber, ampere turns over Weber. Okay, next we are going to Ohm's law for magnetic circuit. So EMF is in electric circuit. In this magnetic circuit, we call MMF. The magnetomotive force MMF, or the unit is F, not the unit, the symbol is F, is proportional to the product of the number of turns around the core in which the flux turns to be established and the current through the turn of wire. So phi or magnetic flux is equals to F or the MMF over reluctance. F or equals to Ni, where N is number of turn of winding in a coil, I is electric current passing through the coil. F ataupun MMF, ability of coil to produce magnetic flux. So when magnetic flux is produced to electric circuit passing the winding, so this is what we call the MMF. Okay. So this is the different Ohm's law for magnetic circuit in electric circuit and in magnetic circuit. You can read it. Okay, magnetic field intensity. Okay, magnetic field intensity is just the MMF per unit length. So it's the MMF or the F just now over the magnetic field, the length of along the path of the flux. So this is the definition and also the formula. H is equals to F over L. H is determined solely by the number of turn and the N, the current I, and the length of the core. So F is equals to Ni, so H is equals to Ni over L. So we list again, B is equals to mu H. So these are the formula that you should remember. You can play around with this formula. Okay, for example, to find the value of L needed to develop a magnetic flux of 4 times 10 to the power of negative 4 Weber. So here you have N equals to 400 turns and A is equals to 2 times 10 power of negative 3. And the permeability of material, which are mu R, is equal to 1.818 times 10 to the power of negative 3 Weber over ampere per meter. So you have to find the L. At first, you can find the B. B equals to phi over A. You have phi here, the magnetic flux, and you also have A. You got 0.2 Tesla. Okay, from that you can find the H. The magnetic field is equals to 110 ampere turns per meter. So now you get F equals to Ni, which is same as HL, and you have all the value except I. Now you can get the I, 44 milli ampere. Just put in the parameters in the formula. Okay, for this type of question, it may comes like this, or it may come ask you to find the flux, ask you to find the B. So you have to play around with the formula. Okay, example 3. A coil of 200 turns is wound uniformly over a wooden ring, having a mean circumference of 600 mm and uniform cross-sectional area of 500 mm squared. If the current through the coil is 4 ampere, calculate magnetic field strength, flux density, and the total flux. Okay, you have to try to do this. Very, very important. So it gives you N is equals to 200. Okay, this is wooden ring. Okay, what you can get in wooden ring? So wooden ring means it's non-magnetic material. The mu, the permeability of the material is 1. So the mu, the total permeability mu is equals to just permeability of the free space, 4 pi times 10 to the power of negative 7. This one is the L, 600 millimeter, and the A is 500 millimeter square, and I is 4 ampere. Okay, you should get this answer. Try yourself. Okay, example 4. A mild steel ring having a cross-sectional area of 500 mm square and mean circumference of 400 mm. So, has a coil of 200 turns, wound uniformly around it. The relative permeability of mild steel for respective flux density is about 380. Find the reluctance and the current required to produce a flux of 800 mu Weber in the ring. Then try to do it. Okay, I leave you to that. Okay, finish part 1. Okay, now we go to hysteresis. This is important concept. So hysteresis is the lagging effect between the flux density B of the material and the magnetizing force H applied. So we can call a hysteresis curve, or we can also BH curve. Some book will call BH curve. So the relationship between B and H, or how the material respond to the magnetic field, which is H lah. So the characteristic of the magnetic properties of the material can be shown in this curve. For example, you can see the blue line from 0 here go up until A and B, right? So this is when we apply the current, it will go up until it reaches saturation. And opposite magnetic field until 0, it can go back and go up and so on. So the hysteresis curve, the shaded area here is called hysteresis curve. And the bigger or the small, how small or how big it is, it depends on the coercivity. The bigger the area, the more hysteresis loss, which is the permanent magnet. Or the small enclosed area, for example, very good like silicon, steel. For example, when we have H is equals to 800, the magnetic field is equal to 800. When the steel score, the B is about 1.2, where for vacuum, it is about only 1 meter. So the shape really depend on the type of or the characteristic of the material. So the normal magnetizing curve for 3 ferromagnetic material, which are steel sheet, here the orange one, second one cast steel, and the third one is cast iron. Okay, these 3 type you always use. This is the normally type that we use. So how to read it? So when we can read from here, the B, for example, 1.2 Tesla. So if the material is sheet steel, okay, we can from 1.2 go until the blue line and the sheet steel. So the orange shaded one, go down, and you can read the value at the uh, y-axis. So how many? So it's more than 300 here. It's like 400 something, right? So that's how you read it from B or from x-axis. You go which one is the type of material, and you read the H value. Okay, Ampere's second law. Ampere's second law is the algebraic sum of the rises and drop of the MMF around a closed loop of a magnetic circuit is equals to 0. So which means same with your circuit theory. So it means if you correlate with the circuit law. So in your mind now, it's like how you read the electric circuit, you can read the magnetic circuit. So the total of MMF must be 0. In a loop, the total must be 0. So and we know that F or MMF is equals to HL. So by applying the relationship of electric circuit, so now F is equals to phi R. This is same like V is equal to IR. However, if F is equal to HL is more practical equation for the MMF drop. This is exactly like your principal conversion of energy, right? Okay, now you look at this. It has two materials. This one is sorry, three materials: iron, steel, and cobalt. And here the carrying current I go into the coil, and the magnetic flux go into the iron, the steel, and the cobalt. So the total F, so because this is closed loop, the total F is equals to 0, where F is equals to HL. However, this has three type of material. So the HL for each type are different. Why different? Because the permeability of different material is different. So the total we have to add three types together. So Ni minus HAB. Okay, we read still first AB, right? But then BC in cobalt and CA as in iron. Okay. HAB, LAB plus HBC, LBC plus HCA, LCA. Okay, the same of the flux, the sum of flux entering a junction is equals to the sum of flux leaving a junction. Okay, this one is same with what? Yes, your Kirchhoff current law, KCL. So we have A here. So flux A is equals to flux B plus flux C. Or like phi A is equal to phi B plus phi C. Or here at B, phi B plus phi C is equals to phi A. This one, how you read is exactly like your KCL. Okay, now we have A gap. Okay, the spreading of a flux line outside the common area of the core for the air gap is known as fringing. Air gap is used to avoid situation to occur in a magnetic material when the current flow is too high, and air gap will increase the reluctance of the magnetic material. Okay, now you see this one, we have a phi C here, have two side, right? Okay, then we will have arrow in the middle. So when the arrow is going downward, that's the common area. So that's the normal error we call air gap. But when the going outside, that one is not normal. We call it fringing. So crossing, going downward, crossing is normal, and not normal is fringing, where in the right and the left side. So if we don't want to make it less accurate, we have to reduce the fluxes. Okay, equivalent magnetic circuit with air gap. Now is the typical magnetic circuit. Okay, the reluctance. So now we have here. So we have to calculate the reluctance, for example. So because of the air gap is here, we have core reluctance and air gap reluctance. So we have two resistance lah, but in magnetic field we call it reluctance. If don't have air gap, we have only core reluctance. But now we have air gap, the total reluctance must be the total of two. Why is it? Because we have different permeability. For the core reluctance, L is equals to mu core over A. For the air gap reluctance, the length of the gap, Lg is equals to mu naught times A. Because the air gap, right, vacuum, so it just we just use the 4 pi times 10 to the power of -7, the constant, the free space one. Okay, this is about the fringing effect. Just now we said the fringing, the at side is not normal. Magnetic flux in the gap. Okay, here at your slide you can see the red one is fringing, while the blue one is the normal air gap. Flux that flow through the air gap will tend to bend from its original direction, where the flux inclined to expand at the fringe. It will cause increase of cross-sectional area of magnetic path in the air gap with respect to the cross-sectional area of the core. Okay, can proceed. Okay, now example 5. Calculate the magnetomotive force F required to produce a flux phi of 0.015 Weber across an air gap, L length of air gap 2.5 mm long, having effective area of 200 centimeter square. So MMF, also F equals to phi R, where phi is equals to 0.15, which is R, L over mu air gap, mu naught. Okay, mu air gap is 1, so just L over mu naught times A. Okay, you should get the answer of 1492 ampere turn. Okay, now we try example 6. Find the flux if the flux density is 1 Tesla, the current in the coil, and the magnetic field intensity in the gap and the magnetic core. Neglect the fringing effect. Okay, now we have magnetic core here, and is equal to 500. So we have current carrying the coil here. It gives you A, length of the air gap, length of the core, and mu R. So first, it asks you to find the flux if flux density is 1. So it gives you B is equals to 1, flux phi B times A. So 1 Tesla times A. It gives you, but you have to know that area of the core is equals to area of the gap. So you got 9 times 10 power of -4 Weber. And then to proceed, you have to find the current in the coil. First, you find the MMF. F is equal to phi R, the reluctance. But the reluctance is different between RC and RG. So the total of F is the FC plus FG. So for the air gap, reluctance of gap is equals to Lg. This one is not C, right? Lg over mu naught Ag, 5 times 10 to the power of negative 4 over 4 pi times 10 negative 7 times area of air gap. So you got 4.42 times 10 power of 5. And then you can put it in the equation. You got for Fg. The same you do it for F core. But for core, you must time for the mu, you must times the mu of the core. So the relative permeability. So then you get the total F, 401.31 ampere turn. So that you already have the F, you can find the A because you have the turn. So I equals to F over N. So you got 0.8 for A. And then the magnetic field intensity in the gap and the magnetic core. Question number 3. The example 6, but the section the number 3. So different is just at the mu. Again, in wooden or in air gap and everything, the mu r is equals to 1. So we can just use the mu. Okay, you can try the example 7. And the figure represents the magnetic circuit of the relay. The coil has 500 turn. So N is equals to 500 turn. The mean core path is LC is equals to 360 mm. When the air gap length are 1.5 millimeter each, so it has two air gap here, a flux density of 0.8 Tesla is required to actuate the relay. So the core is cast steel with the field intensity of 510 ampere turns over meter. Find the current in the coil. So how much the current needed to activate the relay? So here is the answer, 4.19. And permeability of the core, and if the air gap is 0, count. Okay, this one you can try. Okay, now we are going to analyze the circuit. This one is really important. But once you get the concept, just like your electric circuit, you will be able to do it. So, for example, series parallel magnetic circuit. You got the magnetic core like this. How to put into the magnetic circuit? You can draw like this. Okay, this is like we have two loops here. The core is in the middle, so the core is here in the middle as F. And the reluctance, you got second reluctance here and first reluctance S1 and S2. And you don't have the air gap, so here is, this one is S3. So how to read it? You read by loop. For example, the first one, N1 is equal to H3 L3 plus H1 L1, and N1 is equal to H2 L3 plus H2 L2. Just read the loop as in your Kirchhoff laws. Okay, here when the when your coil is at the side, so your FA will be here. So how to read? Same Kirchhoff law. Phi 1 is equal to phi 2 plus phi 3. So you read here first and you read the second loop. The first loop and the second loop. And I is equal to H1 L1 plus H3 L3. H3 L3 is equal to H2 L2. Good. This one we have air gap. The coil is in the middle too, but have air gap. So we have reluctance of air gap here of phi 3. You read it. Loop 1 and because it's here, right? So it has 3 part, H3L3 plus HSLS. Here is denoted, and plus H1L1. For the loop 2, HNI is equal to H3L3 plus HSILS plus H2L2. Okay, for this one, I want you to really cut the concept and try to do your tutorial. Your past year question is really important to try to do it. If you have any question, please reach me. I think until now, thank you. Whatever you can just WhatsApp me, and the next chapter will be continued by Dr. Wui. Thank you and Assalamualaikum.